Hello, this is Dr. Johnson. I am one of the AP Stats teachers at Capella High School. Welcome to this presentation on density curves and the normal distribution. First of all, let me tell you what a density curve is. A density curve is a curve that shows the overall shape of a distribution. Density curves are always on or above the x-axis, so we measure probabilities as being greater than or equal to 0 for all x. The total area under a density curve is always 1. The area under a density curve and above the interval of values in the horizontal axis is the proportion of all observations that fall in that interval. That's important because that tells us that to find probabilities, we can calculate the area under the curve and within a range of numbers. So the fact that the density curve is 1 allows us to calculate probabilities over intervals in a density curve. Histograms. Some histograms approximate a normal distribution. Here you have one. It's not exactly normal, but pretty close. And other distributions are even closer than this one. So sometimes we take a set of data from the real world and we say that it is approximately normal. Within a normal distribution, the following rules apply. Approximately 68% of all data values will lie within 1 standard deviation from the mean. So 68 is within 1 standard deviation of the mean. That's the area shaded in green. 95% of the data will lie within 2 standard deviations of the mean. That's the area shown in green in this graph right here. So that within 2 standard deviations of the mean, we have almost all of the data. And approximately 99.7% of the data lies within 3 standard deviations of the mean. And here I have that graph right here. Now, that tells you, so this leads us to the empirical rule, also called the 68, 95, and the 99.7 rule. Here I have it drawn on this graph right here. 68% is within 1 standard deviation, 95% is within 2, 99% is within 3. But we're going to ask you questions that further subdivide this thing. So I might ask you to calculate the total area that's between minus 2 standard deviations from the mean and positive 1. And so you're going to end up having to add up segments in the distribution using the 68, 95, and 99% rule. As a review, standardizing a normal distribution. Any normal distribution can be standardized, so I can take say a population standard deviation that has a center of 1010 and a standard deviation of 20. And if I standardize every single data point there, I'm going to get this standard normal distribution on the right. So, for example, the 990 on the left corresponds with minus 1 on the right. The 1050 on the left corresponds with positive 2 on the right. And that's what it means to standardize. And this is review 2. If a variable x has a normal distribution with a mean of mu and a standard deviation of sigma, that is, x is distributed normally with mu and sigma as its parameters, then the standardized variable is this right there. That z-score right there has a standard normal distribution. That is, z is distributed normally with a mean of 0 and a standard deviation of 1. And it is called the z-score or the standardized score. Z-scores, here's the principle that I was talking about before. Since the total area under the standard normal distribution is 1, the area under a section of the standard normal distribution curve gives us the probability that an observation falls in that interval. Now, suppose a variable z has a standard normal distribution. That is, z is distributed normally with a mean of 0 and a standard deviation of 1. What is the relative frequency of observations below a particular z. That is, what is the area of that blue blob in the diagram there, the area that is less than or equal to my particular z? Well, the area to the left of z, the area to the left of small letter z, is the relative frequency of getting a random variable less than that particular z, i.e. it is the probability of drawing a z in this range, a random z in this range. Now, determining relative frequency from z-scores, what is the relative frequency that z is less than 1.18? This is going to be a problem because a z of 1.18, 1.18 is not an integer, so I can't use the 68, 95, 99.7 rule. I have to use something else. Well, we're going to use the standard normal table to find this value. Now, I want you at this time, I want you to take a look at the handout that I had you download, and I'm going to show it to you here. The handout was the formula sheet. These are the formulas for AP Statistics, and you will be able to use this formula sheet on all of our tests, and you're able to use this. This will be available to you when you take the AP exam. So this formula sheet has 2 pages of formulas, and then the 3rd page is a Z table. Here's it's called Table A. Here's part of the Table A, and this part right here, it has the first column, the column on the left here, has negative numbers. We want to find the Table A that has positive numbers in the left-hand column. So I'm going to go down one more page like this, and here I have it. Here's my Table A, and all of these columns here have positive Z's right here. And it says here, table entry for Z is the probability lying below a particular Z. So all these areas on the interior here are probabilities. So I'm going to go back to my slides here, and we're going to try and find the probability of getting a random Z less than 1.18. So on your table, I want you to find on the 2nd page of your Table A, this is the side with the positive numbers in your left-hand column. We're going to go down to 1.1, and then we go across to column 0.08. And that gives me a probability of 0.8810 right there. Okay, so that's the probability of getting a random Z less than 1.18. Now, just so you know, the left column lists the Z to the first decimal, that's 1.1 in my example, and the top row has the second decimal, that's 0.08. So the probability of getting a random Z less than 1.18 is 0.8810. Okay, so here's my graph, and I put 0.8, I shade my area to the left of 1.18, and I say probability is 0.8810. What is the relative frequency of getting a random Z less than 1.18? Well, I'm going to write this probability expression. The probability of getting a random Z, my capital Z, less than 1.18 is 0.8810. The capital Z is a random variable Z, and the 1.18 is a particularized value of Z. Now, in a separate video, I'm going to show you how to calculate this number using your calculator, but I've put right here the notation that I want you to put on your answer. Normal CD, and then we're going to have to say that the low, we'll input the low, we're input the upper, we're inputting the standard deviation, and we're inputting the mean. Remember, when we're writing our calculator notation, we have to label all of our inputs: low, upper, standard deviation, and mean. So what is the, let's go back here, I went too fast. Okay, what is the relative frequency of getting a Z greater than 1.18? Well, if the area under the curve is 1, Remember, the total area under the curve is 1. So I can say that the probability of getting a z greater than 1.18 is 1 minus the probability of getting a z less than 1.18. So that's 1 minus 0.8810, and that area right there shaded in white is 0.119. Okay, here's my calculator notation for getting that probability. What is the relative frequency of observations below minus 0.63? Well, if we have a negative z-score, now we have to go to the first page of table A. This is the page that has where the left-hand column is negative numbers, and you can see on my slide right here, it has negative numbers. We want to find the values less than minus 0.63. So on the first page, I go down to minus 0.6, and then I go over to the column that's 0.03, and I find my probability is 0.643 right there. Okay. Did I miss anything? Observations less than mean have negative z-scores. When my particular z is less than 0, I have to use the negative portion of the standard normal table. For continuous random variables x, the probability of getting a random variable x less than a particular a is equal to the probability of getting that x less than or equal to a. This deserves some explanation here. The probability for a strict inequality is the same as a probability for an inequality. Why is that? Well, we're going to say that the probability is 0 for any individual outcome because this is a continuous distribution. The probability of getting a singular outcome is so small that we're going to just say it's 0. We only have positive probabilities for intervals. So that's why I can say that the probability that x is equal to a is 0, and that this equation holds. Now I want to tell you a story here. This is a story about the Red River. The Red River flows north between Minnesota and North Dakota. The levee height is 51 feet. And the National Weather Service back in 1997, they had a lot of snow. And when the weather gets warmer, they predict that the snow is going to melt and eventually make its way to the Red River and flow up to Hudson Bay. On this year, they had so much snow, and the weather was heating up, rather quickly. So they predicted that the river would reach a height of 49 feet. Due to the heavy snowfall in the Great Plains that winter, suppose the National Weather Service predicted the crest to be at Grand Forks to be normally distributed with a mean of 49 and a standard deviation of 4.5 feet. The city's levees were built to handle a flood of 51 feet. What is the probability that the river would breach the levee? Well, first thing I want you to do on this problem, and for that matter on every problem of this type, is to define your variable. So I'm going to let C be the height of the river when it crests. Next thing I want you to do is tell me how C is distributed. C is distributed normally with a mean of 49 and a standard deviation of 45. Now I want to calculate the z-score for the height of interest, 51. So the z-score for a crest height of 51 would be 51 minus 49, all divided by 4.5. That's 0.444. So it's less than half. It's less than half of a standard deviation above the mean. Okay. Now you can't read that all, but the probability of getting a random C, greater than 51, is equal to the probability of getting a Z greater than 0.44. And now you can go to your calculator, or you can go to your table, and you find out that the probability that river will crest at 51 or higher is 0.328. 33% chance that the river will exceed the levee. Here's my calculator notation in normal CD. I plug in on my lower bound of 51. My upper bound is a very large number. Standard deviation of 4.5, a mean of 49, and that tells me that the probability of getting a z greater than 0.44 is 0.328. Okay? I've done the math. What really happened? Do you want to know what really happened in the spring of 1997? Well, in April 1997, the Red River crested at 54 feet and 11 1/100ths of an inch. The water flowed over the levees. It went about 2 miles into the city. There was no loss of life, thankfully, but 50,000 residents had to evacuate, and the cleanup ran into the billions of dollars. The sad story about this is that this could have been prevented. I mean, they know that the snow is going to melt. They have time to take action. They could have, put higher sandbags, increase the height of the levee. They could have diverted some of this water out to the farmlands nearby before the water reached Grand Forks. And there's other steps they could have taken. But the National Weather Service clung to the idea that they only wanted to mention the predicted height that the river would crest at 49 feet. They did not want to mention any uncertainty. They did not want to talk about uncertainty in their estimation because they thought that would make the public skeptical about what the National Weather Service was saying about the mean. So they mentioned nothing about the possibility that it could have been higher or lower. They mentioned nothing about the standard deviation. Well, after this, as you can well imagine, the National Weather Service came under withering criticism for not mentioning anything about the uncertainty, and the National Weather Service has taken this to heart. And I think since then they realize that discussing where the degree of uncertainty is an important part of making a prediction. That's my slide set for today. Thank you very much.